So it turns out, in addition to identifying a compound based on which way it rotates light, we have a more common convention of assigning what are called absolute configurations as opposed to those relative configurations we saw before. And so these absolute configurations are given the designations R and S. And we use what are called the Cahn-Ingold-Prelog rules for giving priorities, and then use those priorities to assign either R or S to every chiral center. So if we take a look at this compound here, both of these, they're enantiomers, it turns out. They are mirror images that are non-superimposable. And there's a chiral center in each one. And if we identify each atom here, so that they're bonded to, so that chiral center is bonded to a carbon here, the chlorine, and then not drawn in, but I'll draw it in. Right behind the chlorine is a hydrogen. Same thing on this one. As a wedged bond, there's a hydrogen, and again the carbon of the methyl and the carbon of the ethyl. And we assign these a priority based on atomic number. And so in this case, chlorine's going to win. So he's number 1, and hydrogen's going to lose. He's number 4. And those are easy. But then we have a tie, and the tie is between carbon and carbon. So in carbon making 4 bonds, each of these carbons is going to have 3 additional bonds besides the one coming from the chiral center. And that's what we're going to rank here. And so this one here is bonded to 3 hydrogens, so we'd rank it as hydrogen, hydrogen, hydrogen. Whereas this carbon right here is bonded to this carbon and then 2 hydrogens not drawn in, so we'd rank it in descending order of atomic number: carbon, hydrogen, hydrogen. And you just go to the first place where you see a difference, and in this case highest atomic number wins. So carbon beats hydrogen. And so this is going to be number 2, and the methyl carbon here is going to be number 3. Same thing on this molecule here. So if you draw now a circle from 1 to 2 to 3, and in this case, that's clockwise, or as I like to say, a right-handed turn if you were turning a steering wheel, and that corresponds to R. And it only corresponds to R if one thing is true, and that one thing has to be that your lowest priority group, the number 4 priority, which is a hydrogen in this case, is in the dashed position, is going away from you. So in this case, this right-handed turn, if you were to face the other side of the molecule, would actually look like a left-handed turn. So it wasn't enough for them to just say left-handed or right-handed turn when you go from 1 to 2 to 3, they had to tell you which side of the molecule to look from. And so in this case, with the lowest priority going away, it's a right-handed turn. That corresponds to R. So it turns out, therefore, clockwise or right-handed turn corresponds to R. So anti-clockwise or counterclockwise or left-handed turn corresponds to S, again, when that lowest priority group is going away from you. We'll take advantage of that here. So in this other molecule here, as you go from 1 to 2 to 3, it looks like a right-handed turn, but your lowest priority group here, that hydrogen, is in the wedged position. It's coming towards you. And so looking at this molecule straight into your screen is the wrong perspective. You should be crawling behind your monitor and looking at the molecule. That way the hydrogen would be going away from you. If you did, what looks like a right-handed turn from this side would look like a left-handed turn. And so this is going to be an S designation for this chiral center. So this is kind of the rule here. So if your lowest priority group is going away from you, right-handed turn for R, left-handed turn for S. If your lowest priority group is in the wedged position coming out of the plane of your screen or your paper, then right-handed turn is S and left-handed turn is R. It's exactly the opposite of the standard designation. So we just talked about your normal designation of R and S occurs when your lowest priority group is in the dashed position going away from you, and how it's just the opposite if it's in the wedge position. The question becomes, though, what happens if your number 4 priority is in the plane? Notice this hydrogen is not attached to a wedge or a dash. So then you've got a couple of options to get creative on how to assign R and S here. So let's take a look. One thing you can do is you can look at the other bond that's in the plane and kind of rotate around that bond. And so we're going to rotate this around that bond. That's going to put this hydrogen where the methyl group is, the methyl where the chlorine is, the chlorine where the hydrogen is, so on and so forth. So they're just going to swap places in a circle. And in this case, that's going to leave us with... So in this case, your hydrogen is now where the methyl is. So your methyl's where the chlorine used to be, and now your chlorine is here. And what's nice is that now your hydrogen is in a position where I can quickly assign R and S. So chlorine's number 1, this carbon was number 2, so this guy's number 3, and as I make my circle, it's a left-handed turn, lowest priority group's in the back, and I can see that this is indeed S. Other approach you can take, and so a lot of students really struggle to rotate that other bond in the plane, so the other approach you might take is you might recall that if I just take and have two groups trade places on a chiral center? And I'm going to leave this chiral center right here as this one right here. I'm going to leave the methyl and the ethyl alone, but I'm going to have the hydrogen and the bromine trade places. And anytime you have two groups trade places on a chiral center, you get the other enantiomer, if it's the only chiral center anyways, but you get the other configuration. R becomes S or S becomes R. So we look at this here, there's 1, there's 2, there's 3, and if you make your circle, this is indeed R. So let's make that a little better. This is R. So, and if we do it on the other side here, 1, 2, 3, it looks like R, but since your hydrogen, the lowest priority group, is on the wedge position, it's the opposite, and so it's really S. So it turns out that's the definition of a stereocenter. It's if you have two groups trade places on a stereocenter and you get a different stereoisomer, that's what makes it a stereocenter. So and that's the case here. We turn the R stereoisomer into the S stereoisomer by having two groups trade places. Now it's not just any, just the wedge and the dash that you can trade. You can have any two groups trade places and it would turn R into S and S into R. And that's going to be the second way I kind of recommend going about looking at assigning priorities here when your lowest priority group, the number 4 priority group, is in the plane. And so what we're going to do here, I'm still going to leave all the wedged bonds and dash bonds and plane bonds in the same place. And what I'm going to do is just have the hydrogen and the methyl trade places. But I'm going to leave the chlorine and the ethyl exactly where they were. And since I've had exactly two groups trade places, then this original compound here on the left and this one on the right are in exactly opposite conformations. So if we assign priorities now to the one on the right, 1, 2, 3, and as we go into our circle, it looks like R, and the lowest priority group's in the back, so it really is R. So, and if this is R, and it's the opposite configuration of original, then therefore original must be S. So there's a third way to approach assigning R and S when your lowest priority group's in the plane. It's not my favorite for undergraduates who haven't had OChem before, but you could try and look at this molecule and change your perspective looking at it from the side, maybe draw a Newman projection. But again, not my personal favorite. It's the one that's kind of most prone to error. But after you've had a year of organic chemistry, it's often the most common and fastest way to go as well. But for now, I'm going to leave that out. Take one of these two, find a way that works for you, and stick with it. So now we're going to take a look at a couple more complicated examples of assigning R and S here. So compound on the right here, we've got a chiral center right there. So, and in this case, he's bonded to a hydrogen that's not drawn in, and that will definitely be priority number 4. So with it being in the back, right-handed term means R, left-handed term means S. But for the other 3, it's bonded to a carbon here, and a carbon here, and we've got a 3-way tie. Now for this carbon on the bottom here, he's bonded to 2 H's and a sulfur, so we'd rank those in descending order of atomic number of sulfur, hydrogen, hydrogen. So for the carbon on the left here, so he's bonded to this carbon over here, and then 2 hydrogens, so we'd rank that as CH. So and then finally the carbon on the right here was only bonded to 2 atoms, bonded to 2 oxygens, but we'll count the double bond twice. And so it'd be oxygen, oxygen, and then a third oxygen. So oxygen, oxygen, oxygen. And this is where we finally see our difference here. And so in this case, a lot of students will ask me, are 3 oxygens better than a sulfur and 2 hydrogens? And that's the wrong question. So the rule says you just find the first point of difference. And the first point of difference is going to compare an oxygen to a sulfur to a carbon, and sulfur is going to win. And so here he's number 1, this carbon with oxygen is number 2, and this carbon with the carbon attached is number 3. And as we go from 1 to 2 to 3, I can see that's counterclockwise, or a left-hand turn, so that corresponds to S. And as our lowest priority group is in the back, that really is S. And here on the right, we've got a maybe even a little bit trickier example, and your chiral center's right here. So, and that chiral center is bonded to a hydrogen that's not drawn in. We'll draw it in the wedged position. And being that the lowest priority, he's going to be priority 4, is in the wedged position. A right-handed turn instead of being R will mean S, and a left-handed turn instead of being S will mean R. And in this case, though, the other 3 atoms are all carbons. So we've got to rank those carbons there. And so if we take a look first at the one on the bottom, that one on the bottom is bonded to 1 carbon and 2 hydrogens. And so we'd rank him as CHH. So if we look at the one on the right, he's bonded to 2 carbon atoms and then 1 hydrogen not drawn in. So we'll rank him as CCH. So, and then this carbon over here is bonded to 1 carbon and 1 hydrogen, but he's got 2 bonds to this carbon, so we'll count it twice, just like we did with the oxygens in the previous example. So this is also going to be CCH. And so we see the first point of difference here leads this guy to lose the battle here, if you will, to the other two, both having carbons in that second position. So this guy's going to be priority number 3, but distinguishing between 1 and 2, we still got a tie here, CCH versus CCH. So now we've got to take this further. So for this guy here, we're going to rank these 2 carbons that we've highlighted in blue. And this one's bonded to 1 additional carbon and 2 H's. So we'd write CH for him. So, and this one right here, again, is bonded to 1 additional carbon going around the chain here and 2 hydrogens, so CH. So, and here's where things are going to get a little bit tricky. For this one, he's bonded to 2 H's, but he doesn't have a third bond. And so what you end up doing is counting one of them back to that previous carbon when you have a double bond like this. So we're still going to rank him as CHH. So, and in this case, it's the same carbon twice, so we actually count it twice for that, CHH, again with the double bond. So in this case, we still have a tie then, CHH, CHH versus CHH, CHH. So, but for this one, we're done. That's the end of the chain. You can't go any deeper. For this one being a ring, you can keep going around the chain, so, and getting more carbons, and so we're going to get more priorities, and that's why he's ultimately going to win. So he's priority number 1, he's priority number 2, and if we make our circle 1 to 2 to 3, it's counterclockwise, which typically corresponds to S, but with our lowest priority group on the wedge position, that's going to correspond to R. Cool. So now let's see how R and S affect nomenclature. So with multiple stereoisomers that could exist, we designate which one you actually have by assigning R and S to any chiral centers. So in this case, we've got a chiral center right here. Before we go there, though, let's just name this just as we would had we not realized it had any chiral centers. And in this case, we'd have numbered 1, 2, 3, 4, 5, 6, the longest chain, and this would have been some form of 2-chlorohexane. So, and our problem comes in realizing that this is a chiral center, that 2-chlorohexane, there are actually 2 different versions of 2-chlorohexane. One where the chiral centers are, and one where he's S, one with this chlorine as the dash, and one with the chlorine as the wedge, as it's drawn. And so in this case, we've got to assign R and S to distinguish between those two. So here, chlorine is going to get the first priority. This carbon over here gets the second. This carbon over here gets the third. And then not drawn in is a hydrogen that's going to get the 4th priority, and it's already in the back. And as we go from 1 to 2 to 3, that's clockwise or a right-handed turn. And so this is going to be in the R configuration. And the way we designate that with one chiral center is you just put R in parentheses at the beginning of the name. Now we'll see in the second example here, we've got 2 chiral centers. So, and it gets a little trickier when you designate them in parentheses at the beginning of the name. So, but once again, if we numbered the longest chain here, we'd number it 1, 2, 3, 4, 5, 6. And so if we were to name this, ignoring the stereochemistry for a minute, we'd have 2-chloro, 3-methyl, hexane. Cool, but now we're going to go through and assign R and S to both chiral centers now. So for chiral center at carbon 2, the chlorine is priority number 1. Carbon on the left is priority 2. Carbon on the right here is priority 3. And not drawn in again is a hydrogen, that's priority 4. So, and if we make our circle from 1 to 2 to 3, that is a right-handed turn. Our lowest priority group's in the back, so that is indeed R. Now if we do the other chiral center now, so for him, the carbon on his right is priority number 1. The carbon on his left is priority number 2. And the methyl carbon up here is priority number 3. And then not drawn in is a hydrogen who gets the 4th priority. And so in this case, with that 4th priority being on the wedge position, whatever this looks like turn-wise, it's the opposite. And so in this case, it looks like a right-handed turn or clockwise, and so that corresponds to R, but again, with the lowest priority group as a wedge, that really is going to correspond to S. And so it turns out when you have many chiral centers here, it's not sufficient just to say R and S in parentheses. You got to be specific and designate which you're referring to. And so we've got a chiral center at carbon 2 of the main chain, and it's in the R configuration, and so we'll say 2R. So, and we've got one at carbon 3 as well in the S configuration. So we don't just say S, we say 3S. And then finish it off from there. So with only one chiral center, you don't have to designate where it is. And I don't say you don't have to. You don't designate where it is. It's obvious. It's the only chiral center. But when you've got multiple chiral centers, you've got to give the numerical designation of where they're located on the parent chain as well.